Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the awesome stuff. This is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Elisa Tau with us today. Hello, Elisa.
Hello everyone. Hello, Francis.
Well, thank
How
you so
are you?
much for agreeing to talk about your very lovely article, which we'll get to.
Thank you for inviting me
Sure.
to talk about it.
Sure. And Elisa, what's your geolocation? Where are you located at?
I'm currently in Chile. I'm doing my PhD at the University of La Serena. So I'm in La Serena right now.
Very cool.
And that's where I did this article that we're going to talk about.
Very cool. And when do you plan on graduating?
Well, hopefully next year. This is
Awesome.
kind of my last year.
Awesome.
So I have to round up my thesis and all that stuff.
Get a few more papers out and all that kind of stuff.
Yeah.
Well, let me be the first then to say, well, I look forward to calling you Dr. Tau in the near future.
Thank you.
You're welcome. Very cool. And Elisa, what do you like to do for research?
Well, my topic is extragalactic astronomy. I study dwarf galaxies, and well, especially I focus on the stellar halo of dwarf galaxies.
Okay.
And well, I normally use hydrodynamical simulations, but well, in this article, it was a side project of my PhD, and we used observational data. So you could say that I'm interested in stellar halos and dwarf galaxies.
Very nice. Very nice. I predict an awesome thesis. And in this fun, we will have a very awesome paper to go through here. And here we go. And this is an AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Extended stellar populations in ultra-faint dwarf galaxies. And Elisa, take us away.
Okay, so again, thank you for inviting me. I have done this article and this research with Caterina Vivas and Clara Martinez Vázquez. And we wanted to, well, study ultrafaint dwarf galaxies, and particularly the possibility of them having extended stellar populations.
Okay.
So that's what this article is about. And let me give you a brief motivation as why do we want to start this. Well, first of all, the stellar halos of Milky Way-like galaxies have been recently studied with a lot of detail from an observational point of view and from a numerical point of view. So this is very interesting because you can think of these stellar halos as a consequence of the hierarchical formation of structures, because these halos can arise from the interaction between galaxies. So, for example, when a galaxy accretes a satellite galaxy, this satellite galaxy will deposit stellar material in the outskirts of the host galaxy, and this will contribute to the accretive part of the stellar halo. And also, these interactions can end up heating up stars of the host galaxy. So these stars can also end up reaching farther orbits from the center and, well, be part of the stellar halo also, just an in situ stellar halo, which means that it's formed of stars that are originally from the host galaxy.
Right. Cool.
So this is like very interesting, and it was, well, mostly studied in Milky Way-like galaxies because, well, they are brighter than dwarf galaxies, and it's easier to observe them. These stellar halos will be less faint than the center of the galaxies. So when we consider dwarf galaxies, well, they are already less faint, less bright than Milky Way-like galaxies, and well, naturally their stellar halos will be even fainter. So with the at least until a few years ago, with the available instrumentation, it was really hard to observe this type of structures.
Yeah.
And well, from a theoretical point of view, it's also hard because to be able to resolve this stellar halos, you need a lot of resolution.
Yes.
And that's very expensive. So, well, in these past few years, there have been new numerical simulations that have improved the resolution.
Okay.
And we are now starting to, well, be able to have reliable results from a theoretical point of view.
Cool.
And so it's a very interesting topic. And in this work, we wanted to try to understand a little bit more about the stellar halos or the possible existence of stellar halos in dwarf galaxies, particularly in ultra-faint dwarf galaxies. And well, what we did was to use our Lyra observations. And why our Lyra observations? So our Lyra are old stars, so you can use them as tracers of population, stellar populations, and you can find them in dwarf galaxies. And also, they are very bright and they can be used as stellar candles. Yes. So that's very important because we can know at which distance this our Lyra are located at. Yes. And that can be helpful to determine if well, they belong to a dwarf galaxy because you can compare the distances in which they are at, and also to well, reduce the foreground contamination of our galaxy. Okay. So, well, that's the motivation of this work. That's why we chose to do it. And well, also Kathy Vivas have already done something similar with less amount of ultra-faint dwarfs, and also not such a profound study, but she tried to do a kind of a survey of our Lyra in ultra-faints. So now we are trying to use this our Lyra in those ultra-faint dwarfs and in more ultra-faint dwarfs that have been discovered recently. Yes. To see if they can be found in the outskirts of the ultra-faint dwarfs. Because if they can be found there, we could say that there are stellar populations in the outskirts of these galaxies. And very recently, like last year, there have been well, various studies that have started to found stars in the outskirts of ultra-faints. Not necessarily around Lyra, but well, it's starting to be well, something very interesting, and you could say that we're starting to find stars in the outskirts of these type of galaxies. Yeah. So what we did was we chose to work with surveys. We used Gaia, CTF, DES, and Pan-STARRS. Okay. And well, specifically, we used the Lyra catalogs of these surveys. Well, each survey has its own advantages and limitations. Yeah. But using all of them, we had a huge sample of our Lyra to start working and to start associating with the ultra-faints that we wanted to study. Got it. Cool. I'm with you. And well, regarding the ultra-faint dwarfs, we used the ultra-faint dwarfs of the Milky Way. So they are Milky Way satellites. And well, we used all of the reported ultra-faint dwarfs, but well, you should know that there are currently more galaxies being discovered that are ultra-faint. They are really hard to discover, so it's like an ongoing topic. It can be updated soon enough. Yes. So, well, what we did was to enhance the sample of ultra-faint dwarf galaxies that Kathy Vivas had studied previously with the ones that have been discovered after she did that work. Okay. And if you go to table 1, you can see like our whole sample of ultrafaint dwarfs.
45. Okay. Okay. Mm-hmm.
Yeah, 45 ultrafaint dwarfs. So here in this table, I'm showing you some characteristics and parameters, basic parameters of these galaxies. And well, they are ordered with respect to their distance from the Milky Way. So you
Okay.
go
Yes.
yeah,
Yes.
from Draco
Thank you.
to I think Colombo. I think it's the
I think
last
this
one,
one
the
is
more
Leo T.
or Leo T,
Yeah.
like the most distant one
Right.
to now.
Wow.
So well, yeah, our final sample of ultrafaint dwarfs consists of 45 galaxies.
Nice.
And well, having the Aralera of the catalogs that I already mentioned, what we did was to try to associate them with these galaxies.
Okay.
And to do that, we followed 3 steps. First of all, we analyzed, we defined a search radius around the galaxy.
Mm-hmm.
So this search radius was of 15 times the half-life radius. The half-life radius is a kind of important parameter in this work because, well, its definition is like the radius within we can find the half of the light of the galaxy. So one half-life radius contains half of the luminosity or the light of the galaxy.
Okay.
And what we did was to analyze 15 times the half-life radius. That was our search radius for each ultrafaint dwarf.
Okay.
Except when this 15 half-life radii was lower than 1 degree in the sky. That could happen for very small galaxies.
Yeah.
So in that case, we used 1 degree as a search radius.
Okay.
So those are layera that were contained within these 15 half-life radii or 1 degree.
Yes.
Were the ones that passed the first step or met the first criterion.
Okay.
And started being candidates for these ultrafaint dwarfs. We then proceeded to analyze the distance, and that's step 2. You can go to, I think it's figure 1.
Yeah, let's go down to figure 1, methodology. Going to be our 3 things. In figure 1, we got 4 of them booties.
Yeah. Okay, so here are some examples of these ultrafaint dwarfs. And what we did is, well, considering the R layera that had already met the first criterion. Okay. Well, we analyzed the distance of these R layera because, as I said, they are standard candles. So this is something that we can obtain, the distance at which they are. And if this distance is well, the same between some error values than the one that the ultrafaint dwarf is located at, then those stars also pass this criterion, this second criterion.
Yes, I'm with you. Okay.
And well, and finally, the last one, the last step, consisted in analyzing the proper-motions of the Aralera and the ultrafaint dwarfs. So this is important because you can have a star that is located at the same, apparently at the same region than the galaxy, but it's not moving in the same either direction or velocity. So you could say that they are not necessarily associated to that galaxy. So if you go to figure 2, I think you can see
final are booties, Ursa.
Yeah, you can see well, examples of our sample, and for example here in Booties 1, what we did was to consider kind of a box with the limits of the proper motions that we were going to consider.
Okay.
So the aura Lyra that well are falling in these boxes or have proper motion errors that allow us to consider them inside of those boxes
Okay.
are the ones that finally met the 3 steps criteria of our selection.
Gotcha.
So this
Gotcha.
final sample of our Lyra are the ones that we're going to consider in this work. And well, they are all associated to different galaxies.
I think this is the final sample here.
Yeah.
Okay, good.
This is the final sample. So we obtained 120 RLIR in 21 different ultrafaint dwarf galaxies.
Nice.
And here, well, the complete sample, you can find it in the machine readable form in the online version of this.
Yeah, so yeah, let's make that the this is only a fraction of the table.
Yeah, it's only a fraction.
Uh-huh.
But well, here we have listed like some of the parameters of these stars, and also well, the identification in each catalog in which we found them, and
Gotcha.
some characteristics.
Mm-hmm.
So
Okay.
once we have this sample, we also have to consider possible contaminants, because, for example, there are some galaxies that can be contaminated by other objects in the sky. An example is Bootes 3 and 1.
Okay.
These galaxies, if you go to figure 5,
Sure.
you can see that they are very close to the Sagittarius string. So here, as you can see,
Okay.
here all the crosses, kind of orange and purple crosses, are the Sagittarius string, are represented the Sagittarius string, and with teal ellipses, you can see Bootes 3, that's the one you're pointed at, and then we have Bootes 1 and 2.
Yeah.
They are all very close to this Sagittarius string.
Mm-hmm.
So in these cases, we have to be very careful, because there can be stars or a layer that we have selected that could belong to the Sagittarius string instead of these galaxies. So that's something we have to take into consideration.
Okay.
Yes. And also, there's also there can also be some galaxies contaminated by the Magellanic clouds. And this is the case of, for example, Delve 2.
Okay.
If you go to figure 7, you can see.
Oh yes, very nice.
You can see that, well, we have these galaxies that are very close to the small Magellanic cloud. So some of them we have analyzed, of course, their magnitudes and the distance and their proper motions. And some of these galaxies that are shown in this figure are not contaminated by the small Magellanic cloud, because for example, the proper motions do not match the ones of the small Magellanic cloud. But for example, Delve 2, it's really hard to distinguish between those Aurora that could belong to Delve 2 or to the small Magellanic cloud. So we also take into consideration this kind of contamination that we could have. Okay, good. Very good. I'm with you. And then also, we also took into consideration the Orphan stream. That's the following figure. So in this case, we have Bootes 2 that, well, it's very near this stream. Yes. So we have to check for the proper motions and the magnitudes of these stars. Okay. Well, we found that out of all of the stars that these that this galaxy has according to our criteria.
Mhm.
Some of them are contaminants and some of them are not. So we also made that point to be sure that we are not considering contaminants in this galaxy.
Yes.
And after doing that, well, we can now focus on which ultrafaint dwarf galaxies have Ara Lyra and which do not have Ara Lyra.
Yes.
And that takes us to table 3.
Table 3. Let's go down to table 3. And here we go. With
Okay.
Lyra. Okay.
Yeah, okay. So we found 120 Ara Lyra in 21 ultrafaint dwarf galaxies, but there are other 24 galaxies in which we did not find any Ara Lyra, because our sample was of a total of 45 ultrafaint dwarfs. So these 24 galaxies that do not have Ara Lyra were classified in 2 groups. The first group is that one that says ultrafaint dwarfs with no Ara Lyra. So all those galaxies do not have Ara Lyra, because if they did, then at least Gaia should be able to detect them. And we did not find them in the in the catalog that Gaia provides.
Yes. Okay, I'm with you.
So then there's another group that consists of ultrafaint dwarfs in which we did not detect any Ara Lyra according to our selection criteria.
Yes.
But that's because, well, our surveys have limitations. So these galaxies do have Ara Lyra. They have been reported in other works. You can see the caption of this table for references, but almost all of them, except for Columba 1, almost all of them have Ara Lyra reported. So
just not.
What we did was to add these ultrafaint dwarfs to our sample. So instead of having 21 ultrafaint dwarfs, we have 30 ultrafaint dwarfs. And we used the information of the Ara Lyra that the other works provided, the ones that reported them. So now instead of having 120 Ara Lyra, we have 216 Ara Lyra, because these galaxies added 96 Ara Lyra to the final sample.
Okay, I'm with you.
And if we only consider the Ara Lyra that we are sure that are not contaminants, because as I said, we had taken into consideration some possibilities of contamination with streams or galaxies, then we have 142 Ara Lyra as a final clean sample without contaminants. So this takes us to the results. So in figure 9, if you have it here. Okay, so
I'm a little too far. Hang on. Okay, I'm with you. Okay.
So in figure 9, we have kind of a histogram of, well, the number of Ara Lyra that we have in different separations. What we did was to compute the separations between the center of the ultrafaint dwarf and the location of these Ara Lyra that we associated to that ultrafaint dwarf. And this was normalized with the half-life radius of each galaxy. And well, this is in the left panel. We can see what we found using all of our sample of Ara Lyra in blue, and in orange we have the clean sample. That means that we don't have contaminants.
Yes, pretty good, pretty good.
And okay, the important thing here is that we are trying to see which of these stars could belong to the stellar halos of the ultrafaint dwarfs. And in this work, we define the stellar halo as the stellar material that a galaxy has outside of 4 times its half-life radius.
Okay.
So everything that can be found outside of 4 half-life radii, that belongs to the stellar halo.
Okay.
But it's important to emphasize that there's not yet a definition for stellar halo. It's kind of in the making. It's not settled yet. So this, of course, varies if you consider another distance. If you, for example, consider the material outside of 3 half-life radii, then you will have more material in this stellar halo than the one that we chose.
Makes sense.
And well, why 4 half-life radii? Well, it's kind of arbitrary, but also we know that inside of 4 half-life radii, we have almost all of the light of the galaxy. So whatever we find outside of 4 half-life radii, it's already the outskirts of that galaxy.
Yes, I'm with you.
Cool. So here in this figure, you can see that there are lots of RLera that are located outside these radius of 4 half-life radii.
Okay.
If you consider all of the RLera, there are even more stars that are located in the outskirts of galaxies. But anyway, if you consider the clean sample to be sure that you don't have any contaminants, there's also a considerable amount of stars that are located outside of the of the galaxy, outside of 4 half-life radii of which dwarf. And well, in the right panel, I'm showing like a zoom in 15 half-life radii, because that was, if you remember, that was like the original cut, the search radius around each galaxy. Yes. But they were a couple of galaxies that were very tiny. So these galaxies are the ones that have RLera, for example, up to 30 something or 60 half-life radii, as shown in the left panel.
Right, right.
But then if you focus on the 15 half-life radii search, you still get lots of stars that are in the outskirts of the galaxies, according to our definition, at least.
Correct.
So once we had seen that these RLera could be located in the outskirts of the ultrafaints, then what we did was to try to see how many of these ultrafaint dwarfs that we were considering have extended populations, have these RLera outside of 4 half-life radii. Okay. So that takes us to figure 10.
Yes, yes.
In which we show
cumulative.
Well, the number of galaxies that we find with extended stellar populations. And well, as kind of a summary of this figure, what we're saying is in blue, we're seeing all the samples, like the 30 ultrafaint dwarfs that we originally considered, between the ones in which I had already found RLera and the ones that we added that had RLera reported, but in which we had not found them. Okay. And in orange, we see the clean sample. So this would be the sample without taking into consideration, for example, Bootes 1 and 3 that I told you about. They were close to the Sagittarius string. Yes. So if we consider all of these that I'm considering, we get that 14 ultrafaint dwarf galaxies have at least one RLera outside 4 half-life radii. So that's like 47% of the whole sample of ultrafaint dwarfs. Okay. But if we consider only the clean sample, just to be sure, we get 10 ultrafaint dwarfs that have at least one RLera outside 4 half-life radii. So that is still an important number, because that's like 33% of the clean sample. Good. Okay. And well, in number, this would be like I think it was 17 RLera. that belong to the outskirts of galaxies in the clean sample. But if we consider all the sample, not only the clean sample, we get 60 RLI outside of these, in the outskirts of these galaxies. And it's important, well, to stress that we're certain that at least in 10 ultrafaint dwarfs, we get extended stellar populations because we find RLI in the outskirts.
Right.
But that's like a lower limit because we are removing some possible contaminants, which we are not sure if they are or not contaminants. To be sure, we should get more data and detailed data of those galaxies and those stars and try to see if they really belong to these galaxies or if they are indeed contaminants. So maybe, for example, if we included Bootes 3, this galaxy has, well, we found a lot of RLA in this galaxy. And well, some of these RLA could be in fact from the galaxy and be located in the outskirts. So that would increase the final number of ultrafaints that we consider to be well, to have stellar halos or extended stellar populations. And then another interesting question for this discussion is, well, how do these stars reach these distances?
Right.
And what we try to do, then I'm showing you in figure 11.
Okay.
We try to see if this distribution had anything to do with the position of these galaxies in their orbit around the Milky Way. So in red, you can see those galaxies in which we found extended stellar populations.
Yes.
And some of them, like Tucana 3, come very close to the Milky Way in their orbit. But some of them are not so close. So if we think about a scenario with tidal stripping and taking these RLA into farther orbits, we could say that it's possible, but it's not the only mechanism by which these stars would reach well, these distances, because some of them are not very near the Milky Way or do not pass really near the Milky Way or do not come so close. So there must be some other mechanism to drive them away.
Yes.
So, well, that's kind of a summary of this work, and the important message to take home is that, well, we found our Lyra in the outskirts of the galaxies, so we can say that ultrafaint dwarfs can have extended stellar populations.
Yes.
Particularly out of our sample, we find that 10 of these ultrafaint dwarf galaxies do have at least one RLA in the outskirts, but this is a lower limit, remember? So we could find more ultrafaint dwarf galaxies with extended stellar populations.
Right.
And well, there was also no preference between the distance of these galaxies from the Milky Way. We found some of them that were very far away and do have extended stellar populations, and some of them that are closer and also have extended stellar populations, so that's not very meaningful. And also the absolute magnitudes of these galaxies vary a lot, so we could not say that the faintest or the brightest ones are the ones that have extended stellar populations.
Right. Right.
And well, these results were in agreement with other studies that have been published recently. This is a very hot topic, and a lot of people are working on this right now. And well, some other authors, such as Weller and Sestito, also found stars that they consider to be in the outskirts of galaxies, of ultrafaint dwarf galaxies. But they all use different definitions for stellar halos, like this distance of from the center of the galaxy. So,
Mhm.
for example, I remember that water to take into consideration, I think it's 2.5 Hawkeye radii. So if we lowered our limit radii to uh, 2 half-life radii, 3 half-life radii, we would certainly have more auroral layer
Yes.
in the outskirts of the galaxies, because we would be considering
Okay.
the beginning of the stellar halo to be closer to the center of the galaxy, because it would be like, I don't know, maybe 3 half-life radii.
Cool.
So that's important. That's
Yes.
we get these results with this definition we chose to work with.
Understood.
And that's the summary of this article.
Very cool. Very, very cool. Beautiful. Elisa, I want to thank you so much for walking us through your very awesome article. It's great.
Thank you. Thank you very much for the opportunity to talk about it.
And you touched on it a little bit there, particularly toward the end. So let me push on it a little bit.
Okay.
So where do you think we go from here, given the published article? Is there more data in the pipe to get more ultra-faint galaxies? Are you going to go back and change your definition of 4 half-lives? Are there other telescopes that could pick up some RR libraries in these ultra-faints, and so on? So maybe there's some theoretical or numerical work that could be done. So just sort of, what do you think are the next steps over the next couple of years?
Yeah, of course. Well, we are currently developing new telescopes and new surveys, so that's very interesting. For example, I can think of the Vera Rubin Observatory that will be hopefully working soon. And that will be very helpful to try to detect and observe these kind of structures, the stellar halos around ultrafaint dwarfs, because it will improve the kind of magnitudes that we can reach. It will be great to use them to study this type of objects. And also from a theoretical point of view, I'm currently, I work with numerical simulations, and in these past years, there has been a lot of improvement in regarding the resolution of these simulations. So I think it's very interesting to study these stellar halos from a theoretical point of view, and it can also bring some insight in the accreted and in situ components of the stellar halo, because when we use simulations, it's easier to know which stars were formed in which galaxy.
Yes, exactly.
And also to analyze where they came from, which mergers contributed to the formation of these structures. So to study them from a theoretical point of view, it's also very important. And I think there are lots of work on that topic right now. And I am currently doing my PhD working with the Auriga simulations, so I'm trying to also understand them from a theoretical point of view.
Nice. Very cool. Very cool. Well, it'll be a lot of fun, and it'll be really interesting over the next couple of years to see this.
Yeah, hopefully.
So it'll be really great. Very cool. Very cool. Elisa, thank you so much once again for walking us through your very lovely article.
Okay, thank you. Thank you for listening. I hope you enjoyed it.
And that will do, everyone. And I hope you did enjoy it. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.